Our third paper is called MegaScale-Infer. It's about efficient MOE serving, and it's given by Ruidong Zhu and Zhao Jin, who are third-year PhD candidates at Peking University, advised by Professor Jin Jin. And they're obviously interested in machine learning. So.
Okay. Hello, everyone. I'm Ruidong Zhu from Peking University. I'm glad to share our work, MegaScale-Infer, efficient mixture of expert serving with disaggregated expert parallelism. This is a joint work of Peking University and Bailang Seed. Driven by scaling laws, state-of-the-art models keep growing larger. Here, we list some of the latest large-scale LLMs, each with hundreds of billions of parameters. Notably, all of them adopt the mixture of experts architecture, MOE, which has become the most effective and mainstream approach to scale the model size. The main reason MOE has become so popular is that it scales model size with little extra computation. In a standard transformer, each layer has two main modules, an attention module and a feed-forward network, FFN. MOE replaces a single FFN with multiple FFNs, each called an expert. A gating function after the attention module in each layer routes the input tokens to a subset of these experts, named top K experts. The final output of the MOE layer is a weighted sum of the selected experts' outputs. The sparse nature of the selected experts' outputs allows for scaling the model size by increasing the number of experts without linearly raising the computational costs. Before diving into MO inference, let's first review the phases of LLM inference. After receiving an input token sequence, the model first performs prefill. Here, it processes the whole sequence and stores the intermediate results, called the KV cache. In the subsequent multiple rounds of the decoding phase, the LLM reuses the KV cache to generate the next token one by one. With a certain sequence length, both attention and FFN computation in the prefill phase can be considered to be compute-intensive. However, the decoding phase is different, since the attention in the decoding phase needs to access the KV cache of all previous tokens. It is generally considered to be memory-intensive. The FFN, on the other hand, can increase its computational intensity through batching, transforming it from memory-intensive into compute-intensive. So, how can we build an efficient MO inference service? Existing solutions mainly rely on two technologies, PD disaggregation and large-scale expert parallelism. PD disaggregation takes note of the different characteristics of the prefill and decoding phase in LLM inference. Collocating these two phases will lead to severe interference. Therefore, it is proposed to execute the two phases on different nodes. This avoids interference and allows us to optimize each phase based on its workload. For example, we can apply different parallel strategies to each phase. Current MO inference service also employs a specialized parallel strategy called expert parallelism. It partitions parameters across GPUs or nodes at the granularity of experts, compared with the tensor parallelism, which requires splitting the parameter matrix. Expert parallelism keeps the complete parameters of each expert. However, tokens must be sent to experts located on different nodes, and the outputs must be gathered back. This requires point-to-point O2O communication. As models grow larger and experts become more numerous but smaller, expert parallelism provides better efficiency and scalability. With PD disaggregation and large-scale expert parallelism, MO inference can already achieve relatively high performance. However, we noticed a serious issue of low GPU utilization during the decoding phase of MO inference. This comes from two factors. On one hand, as we discussed earlier, attention computations represented by GQA are memory intensive. This leads to low GPU utilization. On the other hand, due to the sparsity of MOE, each expert only receives part of the tokens in a batch. Therefore, with the same global batch size, the batch size of the FFN module in MOE is smaller than that of the dense model, leading to lower computational intensity and GPU utilization. As MOE scales up and the sparsity increases, the problem only gets worse. To solve these issues, we propose disaggregating the attention and FFN modules onto different nodes. This brings two benefits. First, after disaggregation, the attention and FFN components can scale independently. The attention side can be deployed using the replication method, allowing requests to be aggregated and sent to the expert side. This increases the batch size of FFN, thereby enhancing its computational efficiency. Second, by disaggregating these two modules with distinct characteristics, we can adopt heterogeneous deployment and choose more cost-effective hardware for each module, reducing the overall cost of the MOE inference. However, disaggregating brings two additional challenges. The first challenge stems from resource idleness caused by computational dependencies. Each request must sequentially run attention and then expert computation for each layer. So, when the system is executing attention of a batch, the expert nodes sit idle, and vice versa. The second challenge is the high communication demand. Unlike PD disaggregation, which adds only one extra communication per request, disaggregating attention and FFN adds two extra communications per layer. Both involves all the attention and expert nodes, with data potentially sent between any pair of them. We call this communication is M2N communication. The latency of M2N must be low to maintain high resource utilization and meet the latency targets. However, using existing libraries like NICO for this only gives poor performance. As shown in this figure, in the simplified 1-to-1 scenario, both the median and tail latency of NICO are much higher than ideal. Next, my co-author Chao will present our design and evaluation.
To fully exploit attention and FFN disaggregation and tackle the two challenges, we propose an efficient MOE inference system called MegaScale-Infer. Its key innovation is disaggregated expert parallelism, which deploys attention and FFN modules separately. We also introduce a ping-pong pipeline to maximize resource usage and a high-performance M2N communication library to reduce extra communication overhead. Under disaggregated expert parallelism, attention and experts are deployed independently. The attention nodes are deployed in a replicated manner, also known as data parallelism, where each node processes different requests. On the other hand, the expert nodes adopt expert parallelism. Each expert receives tokens from multiple attention nodes, which increases the FFN batch size. The ping-pong pipeline splits a batch into multiple macro batches. This allows attention and expert modules to stay busy and overlaps communication with computation. Let's work through an example. First, at each layer, each macro batch will go through 4 steps in sequence: attention computation, network communication from attention to expert, expert computation, and network communication from expert back to attention. In this example, we set up 4 macro batches. They are arranged in sequence and perform computation and communication one after another. The same process repeats layer by layer. As shown in the figure, this keeps both attention and expert modules fully utilized. But to make this work, we need to satisfy specific requirements for the computation time and communication time. This requires us to carefully configure the deployment strategy and implement high-performance network communication. To fully leverage the advantages of disaggregated expert parallelism and the ping-pong pipeline, we search for an optimal deployment plan. Our goal is to maximize throughput per cost while meeting the SLO. We use a simple enumeration algorithm to search for the best configuration under certain constraints. These constraints include the computation times of attention and experts should be close, and the communication time must be less than computation time. There must be enough macro batches to hide the communication latency. GPU memory must fit both parameters and KV cache, etc. Please refer to our paper for more details. We also use heterogeneous deployment with different types of hardware. Here we compare the price and performance of several NVIDIA GPUs. Among them, the H20 offers the best memory capacity and memory bandwidth per cost, making it well suited for attention computation. And the L40S offers the best compute power per cost, so it is ideal for FFN computation. By combining these two GPUs for heterogeneous deployment, we can significantly reduce the cost of MOE inference. All these improvements rely on a high-performance M2N communication library. Only if communication time is lower than the computation latency can the ping-pong pipeline fully overlap communication with computation. So we built a high-performance M2N library. It accelerates the communication by minimizing additional overhead such as data copies, GPU synchronizations, and group operations. On the control plane, the CPU initiates and manages send-receive operations, while on the data plane, data is directly transferred between the GPU and the NIC. We conducted experiments on 2 clusters and 3 models. The first cluster is homogeneous with NVIDIA Ampere GPUs. The second is heterogeneous with both H20 and L40S GPUs. The 3 models share the same structure but differ in the number of parameters and experts. We use VLM and TensorRT-LLM as our baselines. In the case of homogeneous deployment, MegaScale-Infer expands the number of attention nodes through disaggregated expert parallelism. This increases the batch size per expert and improves GPU utilization. Compared with VLM and TensorRT-LLM, it achieves up to 7.11 times and 1.9 times higher per GPU decoding throughput. In heterogeneous deployment, the disaggregated deployment of attention and FFN allows the use of more cost-effective hardware. In contrast, baselines only run on homogeneous nodes. Therefore, compared with VLM and TensorRT-LLM, MegaScale-Infer boosts the per GPU decoding throughput by up to 3.24 times and 1.86 times, respectively. We also evaluated the performance of our M2N communication library. Across different data sizes, it shows an order of magnitude lower median and tail latency compared with NICO. For the same data size, it also delivers higher throughput and better bandwidth utilization. We also studied the impact of the deployment plan on the overall performance by keeping other variables constant and only changing one variable. First, the number of macro batches. With only one macro batch, only one module is active at a time, resulting in low throughput. Increasing the number to 2 allows the resources of both modules to be utilized simultaneously, but the communication overhead can't be overlapped. In our testbed, the network bandwidth is relatively large, so 3 macro batches are enough to fully overlap computation and communication. Further increasing the number of macro batches to 4 will not bring additional benefits. Second, we consider the number of attention nodes. With few attention nodes, the computation time of FFN is shorter than that of attention, leading to imbalance. Therefore, adding more attention nodes can increasing the FFN computation time and balance the two. So we can increase the throughput without raising latency. However, after beyond a threshold, the computation time of FFN begins to exceed that of attention. Further increasing the number of attention nodes can causes imbalance again, leading to an increase in latency and a decrease in the throughput. From the 2 examples above, we see that disaggregated expert parallelism and the ping-pong pipeline require specific deployment plan to achieve the best performance. The disaggregated inference architecture has been launched at ByteDance and is now deployed on a cluster with nearly 10,000 GPUs. During deployment, we make new observations regarding the load balancing for the 2 modules. On the expert side, we observed severe load imbalance across experts Additionally, we found that during decoding, the expert load is relatively stable, and hot versus cold experts does not change quickly. But for prefill, the expert load fluctuates significantly. Therefore, the prefill phase needs a more dynamic and flexible distribution strategy for the experts and tokens. On the attention side, we found that even with the same batch size, different sequence lengths cause variations in computation time across nodes. To address this, we compose the batches based on estimated execution time, which balances the load among attention nodes. To conclude, we propose MegaScale-Infer, an inference framework that disaggregates the attention and FFN modules to achieve efficient inference services for large-scale mixture of experts models. Based on the co-design of disaggregated expert parallelism, we used the ping-pong pipeline to improve resource utilization and search for the optimal configuration. Meanwhile, we implemented a high-performance M2N communication library to reduce network overhead. Thanks for listening. We are glad to take questions.
Hi, nice talk. Could you introduce more details about the traffic pattern between the attention nodes and the expert nodes, and give some design goals to the underlying networking?
Sorry, your question is about the communication between the attention node and the expert node?
Yeah, first the traffic pattern, the second some design goals to the underlying networking.
The design goal of the communication is to let the communication time smaller than the computation time of the both module, including the attention and the expert. And the traffic is, we just described in earlier. It's M2. It means each token from the expert from the attention can be dispatched to any expert. So it's it's like from any node of from any part of the attention node, it can be sent to any node in the expert's side. So it's
okay. Thanks.
Okay, thank you.
There's a question in the back.
James from Meta. I'm wondering what kind of a compute side modification needs to be done for to realize the disaggregating attention and FFN. Is there like zero modification, or there's some modification, or something in between?
Sorry, could you repeat the question again?
So you described that you can disaggregate attention and FFN, right? And then you build a end-to-end library, communication library. I'm wondering on the compute side, on upper in the stack, which like the whole inference stack, does that require any kind of modification? And if so, what kind of modification do you need?
The question is, what modifications do you do to the upper software stack? Do you need anything there?
So I don't think we need. I mean that here we only care about the GPU utilization. So in this work, and we do not consider how we need to modify the upper stack.
Yeah, maybe we can take it offline. But my main question is that do you need any other code modification in the upper stack to realize this? Probably the answer is no, I guess. Yeah. Thank you.
Okay. Thank you.
Last question.
Hi. Yeah, that's talk. It's Kuntan from Huawei. And I like the work here, but one thing I want to, quick question is that you actually discrete the attention part and the FFN part, right? So is that the granularity is, I mean, in your experiments, it's a fine in life? I mean, especially the question is about the instance, how large the instance should be for the attention for the FFN. So if so they can match perfectly.
Okay. I think it mainly depends on both the architecture of the model, such as the expert nodes and the top K size, and also it depends on the hardware. It means the bandwidth and the
And I know, but my question is that possible or in your case?
I think it still needs a search, and it also depends on the workload, means the sequence length of the different batch. Yeah.
Okay. Let's thank our speakers again. Thank you for all the questions.